Alright, we were brought into class today by the song Seether, not the group, just the song, from the album American Thighs, and the artist is Veruca Salt, because today we're talking about how ionic compounds, commonly called salts, form. Alright, so today, ionic bonding. We're going to talk about how it works, because if you've thought about it at all, you should have questions. So we're actually going to, in fairly gross detail, explain the energetics of the ionic bonding or the ionic compound forming process. So from an objective standpoint, by the time we're done with this video or this two videos, you're going to be able to define this new quantity called lattice energy, which is basically how strong the ionic bond is. You're going to be able to rank these lattice energies of ionic compounds given their names and or formulas. And you're going to be able to calculate this new thing called lattice energy of a compound given the appropriate thermodynamic data that you need to calculate it. So let's talk about this. All right, so how have we discussed ionic bonding? Because we've been talking about these almost since the second week of class, way back when we saw each other face to face. And there were a couple of concepts that we threw out and associated with them. Number one was that they're formed from the electrostatic attraction between positively and negatively charged particles. So the idea is that you have sodium ions and chloride ions, and they get together, and if enough of them are present, you get a grain of salt. How did the ions come to be? Well, we talked about the properties of grossly metallic elements and nonmetallic elements. Metallic elements typically don't mind giving up electrons. Nonmetallic elements would rather take them. They get along famously, so there is an electron transfer, ions are made, and boom, salt crystal. But let's talk about the stepwise nature of this process, actually ripping an electron away from, let's say, a metal and having a nonmetal take it up. And maybe it's not that easy. So if you've thought about it, the fact that ionic compounds form at all should almost keep you up at night, given what you know now about certain periodic properties like electron affinities of elements. So let's actually end bonds. So let's break this up. So here, my first example here is the formation of potassium chloride. So KCl here is the active ingredient in no salt. So it turns out it's the chloride that gives you the taste. It's the sodium that gives you the high blood pressure. And KCl is a little bit better than that, but it's less rare, a lot more expensive. So let's talk about this process though. So we're taking 2 moles or 2 potassium atoms, a mole of chlorine, and making 2 moles of potassium chloride solid. So the first thing you have to do is actually make the potassium ions that are present in the final product, the KCl. So this would correspond to, for example, the first ionization energy of potassium. Now, the alkali metals are easy to ionize, but it's still not free. You look that up, and that still is going to cost you 419 kilojoules per mole. And then you have to break, so chlorine, left to its own devices, likes to form Cl2 molecules. So you need to break that bond, and bond breaking always costs energy. And if you look this up in the right table, you find that it costs you specifically 243 kilojoules per mole to break it. And you also have to attach the electron to chlorine. Now you might think, oh, that's not bad. The electron affinities are exothermic for halogens, but it turns out that it only costs you 349 kilojoules per mole. So these numbers just don't add up. This should be a horrifically endothermic process. So here we're talking about a total of having to put in about 660-ish kilojoules per mole and only getting about 350 back. Yet I will tell you that this is a very exothermic process. So if you're thinking this shouldn't happen, it does, what are we missing here? Well, we're missing the fact that the formation of the charged particles can potentially lead to a very large lowering in energy by nature of the electrostatic attraction between the oppositely charged particles. And that's exactly what happens. So for KCl, we have to think about it as being, a bunch of isolated K pluses and Cl minuses with no electron sharing between them, but only in this case, for this very simple piece of salt, a very strong electrostatic attraction between the two ions. Now we're going to go in detail the energetics of the formation of magnesium fluoride. I picked this one because it's a little more complicated than KCl and allows me to explicitly show that one additional complication that is not present in KCl. So now remember that this is going to be, a bunch of magnesium ions and fluoride ions. So let's actually talk about in detail the energetics of this. And if you are taking notes, we're going to make a table that will take up at least half a sheet of paper. So if you're near the end of a sheet, maybe you start a new one. All right, let's have at it. All right, what's shown here is something called a Bornhaber cycle. And our x-axis or y-axis here is enthalpy. And we're going to break this down into hypothetical steps. And using Hess's law, or the fact that enthalpy is a state function, figure out what the overall energetics, or figure out specifically what the lattice energy is of this. So our starting point here are the constituent elements of magnesium fluoride, namely a mole of magnesium and a mole of F2 gas. And that's going to be here. And that by definition, remember, actually on the enthalpy scale is 0, because the enthalpy of formation of elements in their standard states is 0. And that's what both of these are. So now we're going to step by step get to magnesium fluoride, except first we're going to do it in one shot. The enthalpy of formation of magnesium fluoride solid is negative 641 kilojoules per mole. Again, this is something you look up in tables. There's one in the back of your book. So the overall process is exothermic. Now, let's do it step by step. All right, the first thing you need to do, now we're going to use quantities like ionization energy, electron affinity, stuff like that. And if you remember from a week or two ago, that all of these things are defined in terms of gas phase atoms of whatever element we're talking about. So we need to actually get the magnesium into the gas phase. Now, we didn't talk about this before, but that in itself is a pretty nasty step. Energy is required to melt and then vaporize it. Going from solid to gas is sublimation, so you would look up again in a table the enthalpy of sublimation of magnesium. And that table will tell you that it is 140 kilojoules per mole of magnesium. All right, so we put in 147 kilojoules per mole. We have vaporized, or sublimated, we'll say, the magnesium. Now the next thing we have to do is make fluorine atoms. And to do that, we have to break apart the single bond in F2. And so what you would do in this case is you might look up, for example, the bond dissociation energy, often called D, of F2. And you would find that that is 160 kilojoules per mole of F2. All right. Now we need to turn the magnesium from a neutral gas phase atom to a neutral gas phase ion. And in this case, so we'll do that even stepwise as well. We could remove one electron, and this would correspond to the first ionization energy of magnesium. And again, that you look up. and that costs you a whopping 738 kilojoules per mole. But it's not magnesium plus 1 that is in the compound, it's magnesium plus 2. So we need to take out a second electron. That would give us magnesium plus 2, 2 free electrons, and then we still have got the 2 fluorine atoms. And you look up the second ionization energy of magnesium, and that comes in at 1450 kilojoules. So at this point, we have added almost 2,500 kilojoules and not really gotten anything back yet. Now, the last thing we need to do is to transform the neutral fluorine atoms to a fluoride ion, again in the gas phase. That corresponds to the electron affinity of fluorine, and you look that up. And that step is exothermic. And so here's the other complication. You have to think about stoichiometry. The electron affinity for fluorine is 328 kilojoules per mole. And we're actually making 2 moles of fluoride, so we're going to have twice that, or negative 656. And yes, now I realize that this is not exactly to scale. So now we've got magnesium plus 2 ions. We have 2 fluoride ions, or 1 mole and 2 moles. And all that is left now is for these to actually come together to form the solid. And the energy associated with that. So if you do the math, this is about negative 2480 kilojoules. And that quantity is the lattice energy of magnesium fluoride. So how did I get this? Well, I know that overall, going from here to here is exothermic by 641 kilojoules per mole. So remember Hess's law. So whether we go straight down in one shot or whether we go step 1, step 2, step 3, step 4, step 5, step 6, the end result, the sum, has to be the same. So this 147 plus 160 plus 738 plus 1450 plus negative 656 plus negative 2480 is the equals negative 641. So that is that all these steps together add up to this negative 641 kilojoules, and that's actually how we calculate it to be negative 2480 kilojoules per mole of magnesium fluoride. All right, so now that you've kind of seen what this is, graphically, and this, by the way, is referred to as a Bornhaber cycle after the 2 folks that kind of worked this out. So the definition of the lattice energy is the energy associated with the formation of a crystalline lattice of the compound from its gaseous ions. So in this case, for magnesium plus, or mole of magnesium 2 plus, I'm sorry, with 2 moles of fluoride to give you 1 mole of magnesium fluoride, again, the lattice energy here is negative 2840 kilojoules per mole. So it turns out that for pretty much any ionic compound, that the energy that you need to vaporize, sublimate, ionize, atomize, all this stuff is more than recovered by the electrostatic attraction that you gain by arranging the ions in just the right way in that lattice, hence the name. So let's talk about the physics of this for a moment or two.